continue our analysis of common collector amplifier. I explained, and now we will see that why this common collector is called emitter follower. We were doing the R parameter analysis, that is resistance parameters analysis of the small signal amplifiers, and we arrived at the expression for the voltage gain of this emitter follower as A B R E prime plus R E, and where, let me recollect that R E is the effective AC impedance or resistance with emitter. R E prime is dynamic emitter resistance, and this we can calculate. This is one of the parameters in R analysis, and this R E prime is given by approximately as 25 millivolts, and to be exact 26 millivolts divided by I E, where I E is emitter current, emitter DC current in milliamperes. When this is already millivolt, if this is in milliamperes, then this resistance will be in ohms, and this is very small resistance, just it normally varies from say 10 to 40, 50 ohms. Now, there is and this value of gain, obviously it is less than 1, and so A V is less than 1, but because this R E is very high as compared to R E prime, then we will see that A V turns out to be very close to, when we neglect R E prime in the denominator, then this is R E by R E, which is close to 1. And for well designed emitter follower amplifiers, this gain is, for example, practical value is A V 0.99 or 0.998 or so. Now we will talk about the phase relationship between the output and input. That means, whether there is a phase reversal or not in this amplifier. By we have seen that in common emitter amplifier there is a phase reversal. That means, the output has a phase difference of pi with the input, meaning when input signal, because it is all varying, time varying, this is AC signal, and for simplicity we are taking our signals as a sinusoidal AC signal. So, when the input is at the peak positive, then the output will be peak negative, and so on. So, there is a phase reversal. In this amplifier, in emitter follower, the common collector amplifier, there is no phase reversal. That means, and remember that this is the only circuit among the 3, common base, common emitter, common collector is the only one in which we give the input to the base and we take the output from the emitter. The load is put at the emitter. This is the only circuit. In other two, the load is with the collector. So, now gain voltage gain is very close to 1, and as I said, there is no phase reversal, no phase reversal in emitter follower. In emitter follower there is no phase reversal. Now, let us see this from the figure which I have drawn earlier, that this was the figure which we have drawn earlier, where in the common collector circuit, emitter follower circuit, we have replaced the transistor by its small signal simplified model, and this is that model. Now, this is the AC signal, and when this signal is positive, it goes up, then because there is a AC and DC simultaneously. So, this will add up with the DC signal, and hence when the input signal is at peak positive, then there will be the IB, the base current is varying, but it will be maximum at this time, and when base current is maximum, since that base current, as you remember, this is alpha times IC or IE, because I remind that in all small signal amplifiers the IC is very closely equal to the emitter current. These two are equal, AC or DC, this is true for both. So, this is that. So, if the IB increases, then IC will also increase. IB is beta times IC, which is very close to beta times IE. So, if beta being constant, if IB increases, IE also has to increase, and once IE increases, then this voltage will also be high. I repeat, this AC signal is superimposed on the Q point, the DC current and voltages. So, the net base current will be highest when the AC signal is here, and it will be least when it is here. So, now we are talking at the point when the base current is highest, then this positive half of the signal at the peak value will give large value of IB, and since beta is constant, IB increases. So, IE will also increase, and IE increases, then the drop across this, that is the AC voltage which is varying across this, will also be high. What I have said? I have said when this is maximum positive, the output which we take from the emitter, the load we put at emitter, this is also highest positive. Similarly, when it is negative, then base current will be least, accordingly IE will also decrease and this will be least, meaning as I said, no phase reversal, no phase between input and output AC signals. Now, there is no phase reversal, that means the output follows the phase of the input, and also the gain in this is close to 1, gain is 1. So, magnitude is also high, magnitude of output is also the same as the input. That is the reason, that means amplitude and phase of output is same as the amplitude and phase of the input signal, and that is the reason from here the name comes emitter follower. The emitter follows the input signal in phase and magnitude, and hence there is no phase reversal. Now, let us talk other parameters of the emitter follower. Then this is current gain. Current gain. We know that I e emitter current, you remember from where we started the physics of the transistor, that I e splits into two, I b and I e. So, I e is equal to I c plus I b, or and also as we have seen here that I c is equal to beta times I b, from where the fundamental definition of beta comes. Beta is the current gain which is the ratio of I c by I b, and so this equation becomes I e equal to beta I b plus I b. This becomes I e is equal to beta plus 1 into I b. So, the current gain in common emitter amplifier, is A I output current by input current, and output current is I e, input current is I b, and from this equation this comes out to be beta plus 1, which is because beta is high. So, 1 can be neglected, and this is beta. Current gain is high. Now, voltage gain is unity, that means there is no voltage gain, but power gain is the product of current gain and voltage gain, that is A p. The power gain is voltage gain into current gain, and voltage gain for common collector is 1, almost 1. So, 1 into current gain, and current gain is beta. So, this is simply beta, and beta is very high, 100, 200, 300, that means there is a power gain. Now, so in emitter follower, the level of the signal goes up, it raises the power level, though it does not there is no voltage gain, but because of the current gain the strength of the signal goes up beta times in this amplifier. Now, let us talk about the input impedance. The input impedance. If you look this circuit, which is the AC equivalent circuit of the emitter follower, here the difference between this circuit and common emitter circuit was simply that we take the output from the collector, but R e was still there. So, the circuit between base and emitter is the same as in the case of common emitter, and you will recall that if I explained it also very clearly, which I am sure you all followed, that the input impedance looked into the base of this circuit is beta times the impedance available or connected with the or the total impedance as seen by the emitter lead. Now, so in this case we can use the same and Z in the input impedance into base. This is beta times the impedance, and the impedances are the two impedances are in series. This is the AC dynamic emitter resistance and this is Re which we have connected. So, this is Re prime plus Re, and you remember that here this is the impedance which we see here. Here this is Z in base, and for the amplifier it is here, that means Rb. The biasing resistances have also to be considered when we talk of the input impedance of the common emitter or any amplifier in general. This point we discussed in details in the common emitter circuit also. For example, you remember that this was the common emitter circuit, and when we see here this is Z in I base, and when we take the biasing resistances into account, then this is the input impedance of the amplifier. Same here. So, the input impedance of the amplifier will be Z I, input impedance of amplifier, this will be Rb, effective value of load resistance, and if it is the two resistances R1 and R2, then Rb is simply R1 in parallel with R2. So, Rb in parallel with this Z in base, this is the input impedance, and this is quite high because Re will be say 1 kilohertz 1 kilo ohm, and this is, if we neglect even, and this is 100, then you know it becomes 100 kilo ohms, and whatever is Rb through one example we will find out these values. So, this is about the input impedance of the amplifier, and now the output impedance. You will remember that we talked about the 4 basic parameters which are essential for a small signal amplifier. One was the current gain, the voltage gain, and then the two impedances, the input impedance and output impedance. These are most important 4 parameters which characterize an amplifier. Now, the output impedance. Output impedance ZO, output impedance. Let us draw the circuit, the equivalent circuit. How do you determine impedance? For example, if you are given a circuit and you do not know anything about the circuit, just the input terminals are available and output terminals are available. Now, you have to find out the input impedance. If it is input impedance, you apply a small voltage at the input, and what is the current which flows in the circuit, the ratio of the two by Ohm's law will be the input impedance. Similarly, we will have to apply, now we are talking about the output impedance, So, we have to find out, we have to apply a small test signal, a test voltage at the output and find out the current IT, and that will give the output impedance. Let me draw the circuit first. this is the effective biasing resistance, and when we are finding the input impedance, then we apply here a AC test signal Vt, which will send a current It, and the ratio of the two will give the input impedance. And here the input signal Vs has to be reduced to 0, but still it will be in the circuit. So, therefore, its resistance will be in the circuit. You may be little surprised that once we are saying that the input signal has to be reduced to 0, then why we should put this Rs. This is like that suppose you are talking from a mic, whether and it is connected to the amplifier, whether you are speaking or not speaking, that means whether the microphone is in actual use or not, but the resistance of the coil will be in the circuit. So, when we have signal is reduced to 0, but still its source resistance has to be considered. So, this is the circuit, and this resistance is Re and this is Re prime. Now, you remember it was said that input side and output side of the transistor, they are not completely isolated. What we do at the input, it does reflect at the output. What we do at the output is reflected at the input, what we do at the input is reflected at the output. Now, same is here, but broadly speaking, for the time being, even if we neglect this part and we look how much will be the impedance. So, you can see here that this is almost at a ground potential, and as seen at this point, this is ground. If this is ground, then two impedances will be in parallel. This is high resistance, this is low resistance, and I remind that when two resistances, one high resistance and one low resistance, they are in parallel, then the effective resistance, equivalent resistance of this combination will be closer to the smaller resistance, and actually it will be smaller than the small resistance, but it will be closer, the value will be closer to the smaller one. So, that way intuitively we can see that output impedance of emitter follower will be equal to this resistance, because these two resistances are almost they are in parallel. This is high resistance. So, the effective value will be Z0 will be equal to Re prime, which is very low, This is important, and in fact that is one of the biggest application of emitter follower. Input impedance very high, output impedance very low. We will talk about it little later. Now, detailed analysis also comes to this conclusion. I am not taking the detailed analysis, but this can be shown that detailed analysis shows that output impedance is Re in parallel with Re prime plus Rb in parallel with Rs by beta. This is the effect, feedback effect we may say, the effect of these resistances connected at the input of the amplifier on the output impedance. Now, here in this expression, as I said just now, Rb is many times it is several hundred kilo ohms, but normally 10, 20, 40 kilo ohm, and this Rs will be much less than 1 kilo. So, the parallel combination will give you value smaller than Rs. So, closely equal to Rs. So, R B prime RB in parallel with RS is equal to RS, because this is high and this is low resistance, and when divided by beta, beta is 100, 200, so this becomes almost negligible. So, RB in parallel with RS divided by beta is equal to RS by beta, and this is very small, very small. So, we can neglect it. So, then we are left with RE. So, the output impedance becomes equal to Z0, then is very close to RE in parallel with RE prime, because the other term which was with this we found too small and we can neglect it. Now, again this is impedance in kiloohms, this is ohms. So, this parallel combination will give you a value very close to RE prime. This is from where we started logically, that the output impedance is equal to RE prime, and RE prime is very small. So, we have found out all the parameters of the emitter follower. To summarize the emitter follower, the voltage gain AV is very close to 1, and current gain, this is voltage gain, current gain is actually beta plus 1, which we can take as beta, because beta is high, 1 can be neglected. So, this is high. Input impedance, is also very high, and output impedance is very low, very low. In fact, out of the 3 configurations, common base, common emitter and common collector, which is under discussion at the moment, emitter follower has the lowest impedance. Now, as far as the application of emitter follower is concerned, then remember that there is a power gain and input impedance is very high, output impedance is low, very low. So, the biggest application for this amplifier is as a buffer amplifier. By buffer we mean a intermediate between 2 states. So, it is used for matching purposes. This emitter follower is used for matching purposes. What is to be matched, I will just call for matching purposes. So, it is used as a buffer amplifier. We have suppose because in the actual system there are several stages. So, suppose this is the a previous stage and this is the next stage, and this is high load, that means low impedance. Remember this is also one feels high load means high resistance. No, again this I have said earlier also, high load means which takes high power and which will draw high power or will give you high power when the impedance is very low. So, high load means low impedance, and this is the normal amplifier, a voltage amplifier, for example CE stage, and the voltage gain for this is RC, RC is the effective value of the collector impedance, impedance seized by the collector, and this is the effective value of the resistance with the emitter. And now here we connect these two, the high load cannot be connected to this, because this will go in parallel with the outputs, that will reduce RC. RC in parallel with very low impedance, so the gain will fall. That means the performance of this stage amplifier and all previous stages will be affected, and this will go down. So, we can't connect a high load to an amplifier directly, amplifier which has a high output impedance, but common emitter amplifier has a very low impedance as we have seen. So, this can be connected, the input will match with the high impedance here, and the output of very low impedance, low output impedance of the common emitter will match with the high load, that means low impedance of the next stage or maybe load. So, this is one of the major application of the CE amplifier. Now, let us quickly take a example, because unless you can calculate some parameters of the amplifier, our knowledge is incomplete. We cannot handle circuits when it comes to practical solutions. So, taking practical examples is a way of getting acquaintance with that and developing the handling capability in ourselves. So, let us take one example. Let us consider this circuit. This is at the input or at the output, the source and the load, they are always connected with a capacitor coupling we use. This point also we have discussed and we will discuss more later. So, let us consider that this is the source resistance and this is the signal Vs which we have connected through this capacitor to a emitter follower, and this is our load RL, which is say 2K, and this is RE, which is also 2 kilo ohm, and this is 400 kilo ohms. This is the circuit, and it is given for this amplifier, the transistor, the beta is given as 100 and Re prime is given as 5 ohms, and we have to find out the input impedance Zi amplifier, this is to be calculated, and also Z out amplifier, this is to be calculated. So, we have to find out these two impedances in this circuit. Now, see, this is the solution. Above we derived an expression for Z in base, and this was equal to beta Re prime plus Re. So, Re prime, what is Re prime is given, that is the dynamic emitter resistance, which is given as 5 ohms, and Re is the effective impedance as seen by the emitter of the transistor. Now, you remember that in AC analysis all capacitors are taken as shorted. So, this is shorted, then these two resistances will come in parallel, and this is what the emitter is seeing. Therefore, this is equal to RE in parallel with RL, that means 2K in parallel with 2K. Use the formula for parallel combination of resistances. 1 by R is equal to 1 by R1 plus 1 by R2, and find out the value of R. So, this comes out to be RE comes out to be 1 kilo ohm. Therefore, this is and this is very small, whether we consider or we do not consider it, it hardly matters. Few percent, 2, 4, 5 up to 5% variations in electronics, in most of the situations they are acceptable. So, Zi base is 100 beta into Re, which is 1 kilo, that means 100 K. This is the impedance as looked at the base. And for the amplifier, I said this has not yet taken into account the biasing resistances, and it is given in this circuit, which here Rb is 400 K. So, Zi amplifier is equal to 400 K in parallel with Z in base. This is 400 K in parallel with 100 K, and when you again solve it, it will come out to 80 K. So, the input impedance of the amplifier is quite high. Now, the output impedance Z0, we arrived at the expression Re in parallel with Re prime plus Rb in parallel with Rs by beta. This is what we arrived at. We talked about this, and now Rb in parallel with Rs in beta, this is 400 K into 0.5 K divided by 100. So, it comes out to be 5 ohms. Substitute it here, Z0 is Re in parallel with Re prime plus 5 ohms. This is also given 5 ohms here. Therefore, this is Re this is in kilo ohms. So, the effective value will be only this much. Output impedance is is 10 ohms. So, this is the way how we can calculate the impedances for an amplifier. So, this was all about common emitter, common collector amplifier, the emitter follower. The last thing in this amplifier is a small signal common base amplifier. In this circuit, the input is connected, input signal to be amplified is connected to the emitter, and it is connected through a capacitor normally. The output we derive from the collector, and the load is connected to the collector. So, the circuit becomes this. This is R L and output we take from R L, V out, V out. This is the circuit, and this can be redrawn like this. Sorry. This is the circuit. Here we connect the input signal to be amplified and we take output from here with respect to ground. Now, here notice one point, that in the earlier two circuits we could forward biased and reverse bias the junctions by using a single battery. This is not possible in the common base. Common base needs two batteries with opposite polarity, plus VCC minus VEE. So, this circuit needs two batteries, which is again it goes against the about this common base. But anyway, this is not the reason for its very few applications. We will come to that. So, this is the the circuit which can be either drawn in this fashion or it can be drawn in this fashion. These here this between emitter, this is emitter lead E, this is base and this is collector. So, between emitter and base this voltage is VEB with this polarity, and here the collector has the base with this polarity plus minus, this is with minus plus, and the other one is VCB, this is with this polarity. We can draw its AC equivalent, and in AC equivalent these capacitors have to be shorted and DC sources have to be DC voltage sources have to be grounded. So, its AC equivalent circuit simply will be this. Now, to do the AC analysis, for AC analysis we replace this transistor with the small signal model which we have been using in earlier amplifiers also. When we do that, then we get this. Now, here earlier we have seen that this is the current which goes in this common base circuit to the collector. If I e is the emitter current, then to the collector what is available is alpha I e. This is equal to I c, and alpha is close to 1, but less than 1. Now, look here, what will be the input impedance? Input impedance simply these two resistances in parallel. So, the input impedance of common base amplifier is Z I. This is of the amplifier itself. When we take the biasing I into consideration, otherwise it is R e prime, but two are coming in parallel. So, Z I is simply equal to R e in parallel to R e prime, and again the two resistances in parallel, a smaller one will be the real the value which will be very close to this. Hence, Z I is equal to R e prime. R e prime very small, this we have been telling, this is normally 10 to 50 ohms. Little variation came this side on this side, but basically this is the value. Now, so input impedance of the amplifier is very low. This is one big reason that why common base circuit is not used. If this amplifier is connected to a battery, because of the small impedance it will draw lot of current, hence battery life will be very short. If it is connected to the other amplifier stages, as we have been talking as a that shortly when we were talking about the applications of common collector, that is emitter follower, we were talking that this will load this. If this is connected to the other amplifier having high impedance, then it will load, that means the effective gain will be reduced drastically, and hence the performance of the amplifier will be very poor. So, we can't really do that, and that is one reason that it is very rarely used. Now, the output impedance is, look here, the output impedance, these two resistances in parallel. So, Z out is R c prime in parallel with R c. This is the effective impedance as seen by the collector, and this is the resistance of the collector. Now, collector in the amplifier is a reverse bias junction. So, this impedance is very high. So, since R c prime is very high, and why it is very high? Because it is a reverse bias junction. Reverse bias junction has very high impedance from few hundred kilo ohms to meg ohms. So, the effective value will be R c. Effective value of output impedance is equal to R c. This is high. Input impedance for common base very low, output impedance very high. Then the voltage gain. Voltage gain you will see from here, from here the voltage gain is V I, that is the here. If we neglect the source resistance, then V I and V S will be the same, otherwise there will be some drop across V S, and that we are neglecting. So, this will be equal to I E into Z I, and Z I is equal to R E prime. So, this is equal to this into I E. This is the input. Input is, I write again, input signal, input voltage, AC input voltage will be I E into R E prime, and V out will be I C, the collector current which is flowing through the effective resistance R C, the output resistance, and output resistance effective will be this, the current is flowing through this is I C, and the two resistances we have seen output resistance is closely equal to this. So, output voltage is I C into R C into R C. Therefore, the voltage gain is the, and this is equal to the I C in the model, this is alpha I E, they are the same. So, this is alpha I E into R C. So, alpha I E into R C divided by I V I, that is I E into R E prime. Alpha, the current gain, is very close to 1. This we have been talking right from beginning. So, this is 1, and then I E cancels with this I. So, the voltage gain is equal to R C R E prime, which is quite high, because R C quite high, 1 or 2 or 4 kilo ohms, and this is few tens of ohms only. So, gains of 100, 200, 300 are quite possible. In this common base circuit, there is no phase reversal, because very quickly I can draw a circuit and show you that why there won't be a phase reversal. Very quickly I go through it. Now, look here in this circuit, this contains AC and DC both. So, both currents will be there. Now, when this is positive plus, this will reduce this, and so the I E will be reduced, I E reduced. Now, if we collect the output voltage V C B here, V C B is V C C minus I C R C. So, if this is reduced, so I C is also reduced, this factor will be reduced, and this will increase. That means, the output voltage will also be high at the same point when input is high, hence there is no phase change, no phase change in input and output in CB amplifier. To summarize, in this amplifier current gain close to 1, that means no current gain, voltage gain high, input impedance very low, and output impedance is quite high. The input impedance is low, and that is one single reason that it finds very few applications. One of the applications is for matching. If you have to match low impedance at the input and high impedance of a load, very few situations, particularly in high power electronics sometimes you face, then this CB amplifier can be used. CB amplifier is very useful to understand the fundamentals of transistors and the working of the amplifier. This we have done earlier, but as far as the practical applications are concerned, common emitter amplifier is most widely used, and common collector, that is emitter follower, is also used as a buffer amplifier. The another reason for common emitter is common emitter can be cascaded without any buffer stages required.